is late. The house is completely quiet. The monitor glow is basically the only thing lighting up your workspace right now. And if you are anything like the software engineers we were talking to tonight, you are probably staring down a terminal window that just threw, another CDA out of memory error.
Oh yeah, the classic OMEM crash. We have all been there.
Right. You are pushing the absolute limits of your hardware, trying to train a model. You've got your batch sizes dialed in perfectly, and the machine is still just saying, well, no. You are quite literally fighting the physical boundaries of silicon and VRAM. And in that specific battle, your front line isn't necessarily your neural network architecture. It is actually your data types.
Yeah, that is the harsh reality of moving from theory to practice, honestly.
Mhm.
When you are burning the midnight oil trying to build these systems, you realize incredibly quickly that the theoretical infinite math of artificial intelligence eventually has to hit finite physical metal.
Exactly.
You have a fixed amount of memory on that GPU. I mean, if your numbers take up too much physical space, your training run crashes. Full stop.
Which brings us to our mission for this deep dive. We are looking at a really fascinating stack of sources tonight on a concept called mixed precision training. We are going after the holy grail for anyone training models, how you can use significantly less memory, dramatically speed up your training times, and somehow maintain the exact same predictive quality in your final model.
It sounds like a complete paradox to anyone coming from traditional computer science. I mean, in standard software engineering, if you arbitrarily drop the precision of your data, you inherently drop the quality of your output.
Oh,
Right?
absolutely. You get physics engines that glitch out entirely.
Right. You get rounding errors in financial software, you get system crashes. But in deep learning, we are finding out that the rules of the road are just entirely different.
Okay, let's unpack this, because to actually understand how we cheat the system and save all this memory, we have to start at the absolute foundation. We have to look at how numbers are structurally stored in the machine. Traditionally, like everything in these deep learning models, every single weight, every bias, every activation flowing through the layers was stored as a float 32, a standard 32-bit floating point number.
Right. 32 physical ones and zeros for every single parameter. And let's put that into perspective for your VRAM. If you are trying to load a modern 70 billion parameter model and each parameter is 32 bits, which is 4 bytes, that is 280 gigabytes of memory just to hold the weights.
Just the weights.
Yeah, not the optimizer states, not the gradients, not the batch data, just the static model itself. No single GPU on the planet holds that. It is a massive, crushing memory footprint.
So the industry obviously realized we simply couldn't scale if we kept using 32 bits for everything, which naturally leads to the idea of, well, cutting it in half, going to 16 bits. But from what I'm reading in our sources, early attempts at 16-bit math were an absolute nightmare for developers.
Oh, a total nightmare.
Standard Float 16, or FP16, introduced something called loss scaling, which just sounds incredibly tedious. Why was just cutting the bits in half such a disaster?
So to understand the disaster, you have to look at the anatomy of the floating point number itself. Think of it like scientific notation. You have the sign bit, is it positive or negative? Then you have the exponent, which tells you how massive or how microscopic the number is. And finally, you have the mantissa, or the fraction, which gives you the precise decimal detail.
Okay, so standard 32-bit float has one sign bit, 8 bits for the exponent to handle that massive scale, and then 23 bits for the fraction to get that ultra-fine decimal detail.
Exactly. Now, when the industry first tried standard FP16, they chopped the total bits in half. But they gave 5 bits to the exponent and 10 bits to the fraction.
Oh, I see where this is going.
Yeah. By shrinking the exponent from 8 bits down to 5 bits, they absolutely destroyed the numerical range. The format physically couldn't represent numbers smaller than roughly 2 to the negative 24th power. Anything smaller just became 0.
And neural networks deal with incredibly tiny numbers all the time, right? The gradients, like the little mathematical adjustments the model makes to learn, can be microscopic. So if your format turns all those tiny adjustments into zeros, your model just stops learning.
Which is exactly why engineers had to invent loss scaling. They literally had to write extra code to multiply all their numbers by a massive constant like 1,000, just to artificially inflate the tiny numbers so they wouldn't vanish into 0 during the math.
That sounds exhausting.
It was. And then they had to divide them back down later. It was brittle, it required constant tuning, and it was just a headache for anyone trying to reliably train a model.
But then Google Brain came along and said, we are doing this wrong. And that led to the transition to bfloat 16, brain floating point. And looking at the bit allocation here, it is actually brilliantly simple. bfloat16 also uses 16 bits, but instead of crippling the exponent, it keeps the exact same 8-bit exponent as the massive float32 format.
Yeah, it's a fundamental shift in priority.
Yeah.
bfloat16 basically says, we don't actually care about the ultra-fine decimal detail. We care about the range.
Right.
By keeping the 8-bit exponent, bfloat16 can represent the exact same incredibly large and incredibly small numbers as float32. It just has way fewer bits dedicated to the fraction, only 7 bits instead of 23.
So it is aggressively rounding the numbers, but it never loses track of the massive scale. This completely eliminates the need for that horrible loss scaling workaround because the tiny numbers don't vanish anymore. They just get a bit fuzzier. But that brings up a massive conceptual hurdle for me as a developer. Well, if we are throwing away that much precision, going from 23 bits of fraction down to just 7, aren't we injecting a massive amount of noise into the system? Is bfloat16 essentially like compressing an image for the web? You lose some of the pixel-perfect detail, but the overall picture, the range of the image, is practically identical to the human eye, or in this case, to the neural network.
That is a great analogy, and yes, we absolutely are injecting noise. But what's fascinating here is that it highlights a profound, almost philosophical property of neural networks themselves. A neural network is not a pristine calculator computing a rocket trajectory.
Right, it's not trying to land on the moon.
Exactly. It is essentially a giant statistical guessing machine, trying to find directional patterns in a sea of data. It is surprisingly resilient.
So it doesn't actually need microscopic 10 decimal place precision to learn effectively.
Far from it. If an internal weight is supposed to be, say, 0.1234567, but bfloat16 rounds it heavily to just 0.123, the network's overall directional learning, its gradient descent, barely even notices. The mathematical gravity is still pulling it in the exact same direction. The math is robust enough to absorb that slightly fuzzed number and just keep marching toward the solution.
Okay, wait. If the network is really that resilient and bfloat16 saves us half our memory while keeping the scale, why not just throw float32 in the trash entirely? I mean, that is what I would do. Just find and replace everything to 16-bit, slash my memory requirements in half, and call it a day.
And if you did that, your late-night training run would flatline about 20 minutes in. The model would completely stall out.
Wait, really? Why? If the forward pass is fine with fuzzy math, what breaks?
The problem isn't making the predictions. The problem is the updating phase. And this is where we actually get into the mechanics of the mixed precision training. While the network's directional learning is robust, the actual act of adding the tiny gradient update to the existing weight is highly, highly delicate.
Let me see if I can model this out. Let's say we have a weight in our network that is currently set to the number 1.0. The network does a massive batch of processing and decides, okay, to get slightly smarter, I need to update this weight by adding 0.000001 to it.
Perfect scenario. Now, if you are strictly using bfloat16 for absolutely everything, bfloat16 only has 7 bits of precision for that fraction, remember?
Right.
It physically does not have the resolution to represent 1.0 plus that microscopic fraction. When the processor tries to add them together, the tiny number just falls off the edge of the bit depth. The result is exactly 1.0.
Oh, wow. So worse than standard underflow, it is a silent failure.
Completely silent.
The code doesn't crash, the compiler doesn't warn you, the math just rounds the update out of existence, your model stops learning, and you are left staring at flatlining metrics with no idea why your loss curve isn't going down.
Exactly. That is the silent killer of neural network training. And to solve it, the framework doesn't just blindly convert everything to 16-bit. It uses a very specific architectural strategy. It keeps a master copy of all your model's weights in the pristine standard float32 format.
So it holds on to that heavy 32-bit format purely for the sake of the optimizer updates. So when that tiny 0.00000001 update comes along, the float32 master weight has the massive 23-bit fractional resolution to safely catch it, add it, and save the progress without rounding it into oblivion.
That is the core mechanism, yeah. It uses the heavy 32-bit format only when you're carefully adjusting the internal dials, but meanwhile the actual heavy lifting computations, what we call the forward and backward passes, where mountains of data are being multiplied together billions of times a second, those are executed in the lightweight bfloat16.
So it's like keeping the pristine master blueprint of an app safely locked in a vault that's your float32, but handing out quick, lightweight photocopies, your bfloat16, to the developers on the chaotic construction site to actually get the heavy lifting done.
That is exactly it. The master blueprint remains completely mathematically sound, so the whole architecture doesn't silently collapse. But the workers on the site aren't bogged down carrying massive, heady documents everywhere. You cast down to 16-bit for the massive matrix multiplications, then you cast back up to 32-bit to apply the delicate gradient updates. It truly delivers the numerical stability of Float32, paired with the blistering speed and low memory footprint of bfloat16.
But hold on, I need to push back on something here. I understand how this architectural pattern saves us massive amounts of VRAM. It prevents the out-of-memory errors. But our sources are highlighting performance numbers that go way beyond just saving space. They are saying that moving to this mixed precision approach speeds up the actual compute by staggering amounts.
Oh, the numbers are wild. When we look at modern hardware, we aren't just seeing a 2x speedup because the files are half the size. We're seeing numbers like 10 to 16 times more TFLOPS floating point operations per second.
Wait, 10 to 16 times more TFLOPS?
Yeah.
That isn't just an incremental patch note, that's a total paradigm shift.
Yeah.
Are we literally just getting a massive speed multiplier for free just by changing a data type flag in our code? Saving memory makes sense, but simply shuffling smaller data types around in software shouldn't automatically mean a 10x multiplier in raw processing speed unless the physical hardware is actively treating those smaller numbers differently.
If we connect this to the bigger picture, you are hitting on the exact right intuition. It isn't just a software trick. This is where software efficiency meets physical silicon. Modern GPUs, particularly from NVIDIA, have specialized hardware physically baked into the die called Tensor Cores.
And Tensor Cores, I assume, absolutely love reduced precision.
They are completely purpose-built for it. Before Tensor Cores, a GPU would do matrix multiplication, which, by the way, is like 99% of what deep learning is, by multiplying numbers one by one in standard pseudo cores. It was highly flexible, but relatively slow. A tensor core is a specialized piece of hardware that grabs a whole block of numbers, like a 4x4 matrix, and multiplies and accumulates them all in a single physical clock cycle.
That's incredible.
It is, but here is the catch. They are physically wired to ingest 16-bit numbers.
So when you are forcing your model to run purely in standard Float32, you are completely bypassing the most powerful part of the silicon. You are driving a hypercar through side streets.
Exactly. Hardware manufacturers recognized years ago that deep learning math was completely bottlenecked by a level of 32-bit precision that the networks didn't even mathematically need. So they spent billions of dollars designing the physical architecture of modern GPUs around these reduced precision highways. They laid down massive, multi-lane autobahns specifically for 16-bit matrix multiplication.
For the engineer listening right now, this means that adding that simple torch.autocast context manager into your training loop isn't just a clever memory hack to keep your late-night IDE from crashing. It is actively routing your matrix math onto that physical silicon highway. It is unlocking the actual physical capabilities of the GPU that are locked away if you stick strictly to legacy Float32 code.
Yeah, it is the difference between a training run that finishes next Thursday versus a run that finishes before you wake up tomorrow morning. Mixed precision is quite literally a hardware optimization disguised as a software setting.
It is genuinely wild to think about. We cut the memory in half, we purposefully introduce noise into our data types, and the physical hardware rewards us by multiplying our compute speed by 10. But, software engineers are never satisfied. If having the bits from 32 down to 16 gave us this massive leap in capability, the natural engineering instinct is to look at bfloat16 and ask, how low can we go before the math entirely shatters?
You just push the system until the whole thing breaks.
Yeah.
And that brings us to the absolute bleeding edge of the AI industry today.
The current frontier of training FP8, 8-bit floating point. We are talking about a data type so intensely small it feels like we are coding for a Super Nintendo. But according to the research notes, FP8 is rapidly emerging as the new gold standard for training massive frontier models.
And the economic motivation is exactly the same as the jump from 32 to 16. By halving the bits again, from 16 bits down to 8, you get another 2x speedup on those tensor cores, you have your memory bandwidth requirements again, and you double your throughput all over again.
Okay, but scaling every single tensor individually sounds like an absolute headache for the developer. At 8 bits, aren't we walking a tightrope where the math becomes too fragile to be useful? I mean, I have to look at the sheer physics of an 8-bit number. 8 bits means you only have 256 possible values to represent everything. How do you possibly fit the sweeping, complex mathematical gradients of a billion-parameter neural network into 256 discrete buckets without utterly destroying the model's ability to learn?
It is incredibly brittle. At 8 bits, you have almost no range, and you have almost no decimal precision. If you just naively dump your network's numbers into an FP8 format, you will instantly get massive overflow, where the numbers are too big, and max out the format, or underflow, where they just vanish into zero. The training run will collapse instantly.
So how is the industry actually making it work? Our sources mention a technique required for FP8 called, quote, careful per-tensor scaling. But they don't really explain the mechanism. Like I said, scaling every single block of numbers individually just sounds like an absolute computational nightmare.
It is a massive engineering overhead, but it is actually brilliant. Think of the 8-bit format like a tiny, rigid window, and your numbers are a vast landscape. Per-tensor scaling means the system literally has to pause, look at a specific block of numbers, a tensor, find the absolute largest mathematical value in that block, and calculate a custom scaling factor.
Okay, so it finds the peak.
Right. It then uses that factor to stretch or shrink the entire distribution of numbers so they perfectly dynamically fit into that tiny 8-bit window without spilling over.
Oh, I see. It is like dynamically adjusting the gain volume on an incredibly sensitive microphone every single millisecond. If the audio gets too loud, you rapidly turn the volume down so the signal doesn't peak and distort. If it gets too quiet, you crank the volume up so it doesn't drop into static. You are constantly shifting the data to fit the hardware's limited dynamic range.
That is the exact mechanism. You dynamically scale the numbers up, do the blistering fast 8-bit matrix multiplication on the tensor cores, and then you use that exact same scaling factor to scale the results back down to their true mathematical value before moving to the next layer.
But the compute overhead of scanning every tensor, finding the max value, calculating the scale, shifting the numbers, doesn't all of that dynamic management eat into the speed gains of using 8 bits in the first place?
It does eat into it, yeah. You don't get a perfect pure 2x speedup in reality because of that management overhead.
Yeah.
But when you are training a frontier model on a cluster of 10,000 H100 GPUs, even a net 1.5x speedup saves millions of dollars in compute costs and weeks of wall clock training time.
Millions of dollars. Wow.
Exactly. The engineering headache of dynamic scaling is absolutely worth the squeeze.
It is just incredible to step back and look at the grand historical timeline of this efficiency evolution. We started at standard FP32 using massive amounts of VRAM. Then we realized we could drop to FP16, but we had to suffer through manual loss scaling. Then Google optimized the exponent and gave us BF16, which solved the scaling issue and unlocked the tensor cores. And now we're dynamically shifting numbers millisecond by millisecond just to cram them into FP8.
And when you look at that whole trajectory from FP32 down to FP8, this evolution of data types has provided roughly a 4 to 8 times cumulative improvement in pure training efficiency.
And that efficiency is totally independent of the actual hardware clock speeds getting faster or architectures getting denser. That massive multiplier is derived purely from us being smarter about how we physically store numbers in memory. We haven't just built a faster engine, we have fundamentally learned how to drastically lighten the fuel.
Which brings it all back to the engineer sitting at the terminal tonight. Understanding the architecture of your data types is no longer just deep computer science trivia. It is the core lever you pull to scale your work.
Absolutely.
Mastering this progression from the mathematical stability of your Float 32 master weights to the B-Float 16 workhorses doing the heavy lifting, right down to the bleeding edge of FP8 tensor scaling, is the secret to maximizing whatever GPU budget you have. It is fundamentally how you train a bigger, smarter model on the hardware sitting right in front of you.
It truly is the difference between a model that takes a month to train and stalls out your project and a model that takes a week and gets you to the next iteration. But as we wrap up this deep dive, we have to acknowledge that this incredibly fast, low-precision, hardware-accelerated math is essentially just an engine block.
Right?
An engine, no matter how fast it spins, needs a steering wheel. It needs a directional signal telling it where to go and what to learn. And that is exactly what we are teasing for our next deep dive. Tomorrow, we are looking into the loss function itself, specifically cross entropy loss.
The loss function is the ultimate signal. Cross entropy loss is the mathematical compass that tells the model exactly how far its predictions are from reality. It takes all of this blistering fast 8-bit and 16-bit math and actually gives it a directional purpose.
Understanding cross-entropy deeply reveals why certain training behaviors emerge, why models hallucinate, and how you, as a practitioner, can actually diagnose the problem when this whole complex system goes off the rails. It's the compass for all of this compute.
But as we close the book on mixed precision tonight, it raises an incredibly profound question as we look at the trajectory of where we are heading. We've watched precision shrink from 32 bits down to 16 and now dynamically cram down into 8 bits, all while somehow maintaining the exact same model quality and intelligence. It raises a fascinating thought for your own engineering journey. What is the absolute theoretical minimum bit depth a neural network actually needs to learn the complex patterns of the universe before the data just irrevocably dissolves into pure random noise?